let's talk about robust AI for embedded virtual sensors. First thing I would like to say is that this work is collaborative work. It's not only myself. It's also Maxime Rosano and Olivier Flebus, we are all together in the same division, which is Advanced Innovation. So let's dive into this topic. My suggestion is to first start with a motivation. So why are we interested into robust AI? We will explore the different solutions. After that, we are going to try to compare them, but for that we need methodology. So we will dive into this in the section 3. After that, we'll compare each of these algorithms and we'll have a short conclusion. So let's start with the motivation. So Schaeffler is an automotive company. They provide plenty of car pieces, but mainly, for instance, we have sensoric and control units. We also provide some solution for thermal management and control system. And typically, this thermal management rely on some inputs which can be provided through sensors. But sometimes the sensors cannot be placed in the car because you don't have the space, for instance. So we try more and more to develop what we call virtual sensors. And later on, this virtual sensor will be used for instance, thermal management system. So to introduce a little bit the use case, I will introduce two characters, fictive character, but this is a real industrial use case. So let's assume we have Bob, which is a product manager. And actually, what he needs is a virtual sensor for temperature estimation. So the good news is he has already collected some data. So he asked Julia, the data scientist, to basically work on it. So first sight looks everything okay. We'll develop a machine learning model, which will be embedded later on. The only issue is that actually the data we collected, even if it was on test rig or whatever, we cannot rely on how accurate it is, meaning that each of our inputs are subject to noise. And so he is worried because what we need is to have a reliable prediction. So one thing we could do is to say that, okay, in my data sets, I will just add some noise in the input features. And you'll see that even when we add noise, the deviation is acceptable, meaning that the prediction remains the same. But the thing is, Bob is not super convinced, actually. It's not a formal proof. And by the way, it works for your kind of noise, but this doesn't provide me any guarantee for all kinds of noises. And so starting to this point, you have two options. Either you have robust AI in your toolkit, or you just say, trust me, I'm a data scientist, right? So we'll explore the different solutions to avoid this argument here. So this was the motivation. So the industrial use case was the following. We have an electric machine over there, and we have 360 hours of recording, temperature recording. We put different captors over there. So here you have the different sensor position. And we have very different kind of cycles to play, okay? We have the Artemis cycle, we have the WLTC cycle. We have plenty of different cycles. And obviously, the final objective is to train a surrogate model which will provide the different temperature estimation. For this, the neural network can rely on different inputs provided by other sensors, typically, which are described here. I will not dive into it too much. But what we are trying to tackle here is to be sure that our machine learning model will be robust against the noise. Okay? If you have any question, please don't hesitate to tell me. I'd rather an attractive discussion, so don't hesitate. Okay, so that's the motivation, okay? We want to find algorithms which are robust over noise, which can convince Bob, our product manager, to think, okay, this is safe. The very first family that we are going to look at is the uncertainty quantification family. So basically, the idea is the following: you have a new input, which will be which will feed the uncertainty machine learning model, and basically you're gonna have a gate here of uncertainty quantification, which will basically say, okay, I'm quite confident here, so you are going to accept the prediction, or you have very high uncertainty, and basically it means that the model says, I don't know. So in this case, you might refuse the prediction and maybe rely on another model, maybe simpler, maybe less accurate, but at least you know it's good enough for pretty much all the situation. Okay, so uncertainty quantification, it's for all use cases where the I don't know is a better prediction than a wrong guess. So uncertainties basically can come from two sources. So let's take a very easy example. Let's assume this is your ground truth function. Okay, so this is what you're trying to modelize. Obviously, when you are here, it's perfect, right? So you have plenty of points which are consistent with each other, so everything looks fine. But obviously, when you are here, so kind of out of distribution, yeah, you expect the uncertainty to rise, right? Because you don't know what happens here. Okay, here it looks quite linear, but what happens here? You don't know that. And so what you would like intuitively is that the uncertainty rise. You have another case where the uncertainty should rise. It's when it's called the aleatoric uncertainty, at the opposite of the epistemic uncertainty. You don't have any data. Here you have data. You have data, but they are really not consistent with each other, meaning that you have a big variance over your target with respect to the variance over your input. What does it mean? It means that this feature alone cannot explain all the variance over there. So you can still add data if you want, but it will not help you because you don't have enough explicative features to correctly fit your ground truth data. The good news is that we can estimate both of them, either the epistemic or the aleatoric, or both of them. And to do that, you can rely on basically two families. The one which provide directly an uncertainty quantification. So think about Bayesian neural network, Gaussian process, or maybe heterostic head for standard neural network. Or you have what we call post hoc solution, meaning that you have a machine learning model already available, and you just want to do some post-processing in order to quantify the uncertainty. So think about conformal prediction or Laplace approximation, for instance. Okay, so that's the first family. Second family of solution is all the broad family of scientific machine learning. But what we know the best is the physics-informed neural network. So for the person who don't know what is physics-informed neural network, think about embedding data-driven approach with physics law. So for example, let's assume you throw a ball over there and you want to predict the trajectory. But you collect only point here, all right? This is only the point you've been collected. From a neural network perspective, for a data-driven perspective, there is no reason to provide a trajectory which will fall eventually, right? Because from a pure data point of view, this is supposed to rise, so you cannot expect anything else. That being said, you know that the ball will eventually fall because you know some laws, some physics law. And actually what you can do is basically plug them in the loss function to minimize the physics loss, the PDA loss here, and your data-driven approach, and your data-driven loss, okay? So at the end of the day, your loss function, composed by these terms, will satisfy the data-driven and the loss, and the physical quantity. In our case, for these industrial use cases, we don't have any physical law to embed, but what we did as PDE loss is just a penalization over the gradients. The intuition was to say that when I slightly change from a point, I don't want a tremendous variation. So it's still a soft constraint. Maybe this is not a hard a bulletproof guarantee, but it just emphasizes the fact that we rely on a very smooth surface response. Okay, so scientific machine learning. But as I said, this is not a provable guarantee, right? This is not a hard constraint. Here we are going to talk about algorithm which will allow us to have this. The intuition, once again, is with a simple example. So think about this image. So the introduction is for adversarial attack. So you have a neural network, okay, which take as input such image and will predict what animal it is. So for instance, here pandas. But the thing is, when you are going to add tiny noise, so a specific tiny noise in this case, you can see the difference, right? The human eye cannot see the difference between these two images here, but still the neural network will provide something very different. And that's exactly the point we are going to tackle in this industrial use case, right? Well, what we want to say is that no matter the noise, if we add a tiny noise, we want a proof that this will not change the prediction, or not too much, okay? You have other kind of attacks, for example, the poisoning attack, where you mislabel some data. But we are very more focused into a regression here, so maybe more something like this. Okay, so to tackle this issue, what we leveraged was an algorithm named Lipschitz neural network. So basically, the idea of Lipschitz neural network is to develop a neural network which will respect the Lipschitz property here. And what is the Lipschitz property? It's basically to say that whatever x1 and x2 in your input space, the answer by your neural network will be bounded by a specific value. So now, if you take, for instance, x2, which is equal to x1 plus a tiny noise, so exactly this. Okay, x2 is equal to x1 plus a tiny noise. What you want to have as property is that the answer provided by your neural network is bounded with an upper bound by the constant of Lipschitz. And that's exactly what we want here. The question you could ask now is, okay, which constant should I put? And this is a little bit trickier, right? Because if your Lipschitz constant is kind of large, actually your network is not constrained enough. Okay, actually your network can vary a lot and can do plenty of crazy things. While if you have a too small constant here, it's over regularized. Okay, so it will output maybe a straight line or something like this. So you have to find something which is appropriate here. And the way to see it, I like to see it actually, is that from a given point, the bigger k is, the larger actually the whole possible area are available. And so what does that mean? It means that if you have you have set a k of Lipschitz like this, and your point is at my cursor over there, actually your neural network cannot reach it. It's impossible by design. So once again, finding a good k is super tricky, at least super important. Okay, and now last family of solution, the symbolic regression. So at least here we don't have anymore a black box. You have an analytical formula. So you can directly rely on the formula to characterize it and so on. So for this family, I'm going to show you two algorithms. The first one is PySR provided by Miles Kramer. So basically it's a genetic algorithm, okay, under the hood, which will try to mix your different features, your different function, unit operation, and so on. And so like a very standard genetic algorithm, it will find the best equation which will fit your data. Just a side note, this package, so it's open source, no worries, The backend is in Julia, though, just so you know. Another algorithm is the Kolmogorov-Arnold network, which is my favorite algorithm of all the algorithms we are going to see. And it's super interesting because it relies on the Kolmogorov-Arnold representation theorem, which stands that if f is a multivariate continuous function on a bounded domain, whatever it is, as complicated you want, as long as it's continuous, then it can be written as a finite composition of continuous function of a single variable and the binary operation. And that's super interesting because actually what the people said about this for the neural network is that instead of training the weight as usual here and the single activation function, we are going to train the activation function itself. So actually, each of them over there are activation function here. Okay? So what does look like is instead of having a weight, a scalar value, you are going to train, maybe this will be a linear, maybe this will be a quadratic, and so on and so forth. And so at the end, when you compose some function, you'll have an analytical formula. So yeah, it's once again, it's a white box. Okay, if you get a little lost after these presentations, these slides, I have a cheat sheet, okay? So first solution we explored was uncertainty quantification. So this will provide a prediction interval. So it's admitting ignorance. You can rely also on scientific machine learning. So I talked about physics informed, but you can rely also on symmetry and so on. To have a robust mathematical guarantee that your model is going to behave like you want, you have formal guarantees, and you have Lipschitz neural network is the algorithm we are going to use. And after that, discovering laws through symbolic regression. Okay, so
Laurent, I think you have a question in the chat. Since you said that we can interrupt you, I think I'm gonna ask it, or maybe Bertrand, you can ask it yourself if you.
No problem. Just I wanted to ask you if there is any question of computation when you move from standard networks to training the function themselves to moving to Kolmogorov. Is this computationally more demanding or is it just the same?
So at the end of the presentation, I have a table which will say how long it is to train and so on.
So I wait until the end. Thank you.
But short answer, yes, it's more expensive.
Yeah, I also have some questions on the limits of all of these parts, like in the on the Lipschitz neural networks, on the confidence intervals, but maybe I'll also wait for the end.
Okay, perfect. All right, so if I try to sum up, we understand that we have an industrial use case where we need a robust AI for Bob, okay, for our product manager. And so far, we have founded 4 kind of solutions. And now we are going to compare them, but it's not that straightforward. And we are going to see it. So let's dive a little bit into the data itself. What you have to understand is that when we go to the test rig, we have different kind of cycles to play. We call them scenarios. Each of these scenarios are different, but some of them looks really similar. For instance, these two looks like really similar, and these two looks really similar. So when we decided to do the training and testing split, we wanted to actually isolate different clusters of cycles to be sure that there is no data leakage in a way. So to do that, what we did is we computed a distance between the time series, each of them, and compute a distance between time series can be a little bit more trickier than we thought, but what we used in this case was a dynamic time wrapping distance, which basically realign the time series in order to find the minimal Euclidean distance. And from this distance, we computed the matrix of the distance. So distance with cycle 1 versus cycle 2, cycle 1 versus cycle 3, cycle 1 versus cycle 4, and so on. And from this distance matrix, we computed the dendrogram. And from that, we got the different clusters. And so what we decided is to isolate the different clusters. Some of full entire clusters were assigned to the training, while other were assigned to the testing set. Okay, so to be sure there was no, once again, data leakage. That being said, when we look at the distribution of the data itself, we saw that actually the training and the testing, they have really similar distribution. So despite this splitting, we didn't really add out of distribution cycle, so to say. So this is maybe a weakness of our approach here. I think it was important to say it out loud. But okay, we have a training set, we have a testing set, we have the different algorithm. So now, how are we going to compare the performance? So for doing that, we will rely on 3 metrics. The first one is obviously the raw performance. It's a prediction. Okay, we're trying to predict a temperature, a scalar, to each time step. So a very standard KPI is the mean square error. Another thing we looked at is the smoothness of the cycle. So basically, if our neural network will output something which is very smooth, we'd rather this, because we know that temperature do not vary super quickly. So this is something we had a look by computing the mean absolute temporal derivative. Okay, and the last and the most interesting one was the robustness approach. By computing the formal bound spread. What the heck it is? So what we rely on another tool, which is Decommon. Actually, the name of the tool is Decommon. It's an open source tool library, Python library under the Airbus GitHub. It was a collaborative work between Anity and Airbus, and so. Basically, what this tool does, it will take as input a box of perturbation. So you say, hey, this is my input. This is all the variation which is possible. So you define your input box. Decommon will take it as input along your neural network model. And it will give you back an interval of all the prediction possible. So this is done with interval-bound propagation algorithm. Actually, there are plenty of different methods to do it. But what you have to remember is that when you give your box, your input, and your model, you'll have a certified way to say that all the prediction which fall into my box will fall into this interval here. There is no way something is outside this overlap, this interval here. And so what we expect? We expect that the smoother the neural network is, the tighter the bound is, all right? Because if your neural network is well not designed, you could expect that a tiny noise could lead to a big variation, all right? So obviously the range of Decommon will be very much broader in a way. Okay, so all of this, we are going to compute everything here. And all these methods, obviously, are compared with a standard vanilla neural network. Right. So we have our methodology. Now let's talk about the performance itself. So this is the ugliest slide of the presentation, so I apologize for that. Okay, what do we have here? Let's take it slowly. Here you have all the algorithm on network architecture. Okay, so vanilla neural network, Bayesian neural network, the gradient regularization, and the Lipschitz. Here it's basically the different symbolic regression approach. Okay, so the linear regression is a symbolic approach, right? Because at the end you have an analytical formula in a way. We have PySR and we have the Kolmogorov-Arnold network. Here you have the different metrics which are used to compare our algorithm. Okay, so the mean square error, the mean derivative, and the spread provided by the command. In addition, we have also the time for training and to predict. This is in relative time, obviously. So the reference is the vanilla. So for instance, the Bayesian neural network takes 50 times longer to train than the vanilla in our experiment. Okay. So what do we see here? We see two things. First, the vanilla neural network is the one which achieves the best raw performance, which is something we could expect, right? Because the vanilla neural network is the algorithm which is not constrained at all. Okay, so it has all the freedom to feed the data. And as we saw that the testing set is kind of in distribution with the training set, this is not strange, basically. That being said, it also has the worst guarantees in terms of perturbation. So the spread, for instance, is the worst, basically, of the other algorithm. At the opposite, the Lipschitz is the one which has the worst performance in terms of neural network prediction, while it has the best spread computed by the command. Okay. Some other information. PySR, for instance, is super long to train. Actually, it takes forever. Basically, we have to do some early stopping, otherwise it's too long. It slightly get better than the linear regression, but we will come back to this later. Unfortunately, for me, the Kolmogorov Arnold network completely failed. And to be honest, I don't know why. But I have to find a why, but currently I don't understand. Okay, that's the raw results. So now let's look a little bit into each of these results a little bit. So this is the uncertainty versus the mean square error. So what you have to understand is that most of the time for the uncertainty quantification, what you will have is a distribution. Okay, so for instance, you're gonna have for a specific point is going to say, okay, I think for this point the prediction will be 50 degrees. It's actually be a normal distribution of average 15 and standard deviation 5, for instance. So when you have a density probability function, you can compute kind of a confidence interval by looking at twice the standard deviation. And basically what you can say to Bob is that when the algorithm is going to predict, it's going to say, okay, the prediction is 50 degrees plus minus 5 degrees at 95% confidence. And based on this, it's up to like the subject matter expert to say this is too big or not. For instance, in this case, something which could be acceptable was a range of 5 degrees. So if our uncertainty quantification has a range under 5 degrees, we accepted the prediction, while if it was above 5 degrees, we rejected it. And in this specific case, it was roughly 55% of accepted and 15% rejected. To do that, we train a Bayesian neural network by optimizing what we call the L bolus. Okay, if you have done any variational autoencoder, it's pretty much the same idea. Instead of training this for only the latent space, you do it for all the weight of your network. So you are going to sample over the weight, and to assess the quality of the uncertainty, what we kind of used to do is computed the correlation, so either Pearson or Spearman, to assess if the uncertainty makes sense, right? Because what you would expect from the uncertainty is that when it rises, the error rises also. Okay. When it's really wrong, you expect that there are a high uncertainty. For the Lipschitz performance, we achieve very good result in a way compared to the vanilla one. So not as good as the vanilla, but very close. And for that, we use a tool that was provided by the DIL library, which is basically consortium or association with ERT Saint-Exupéry, ANITI, and also some Quebec universities and industrial as well. But yeah, it's not super straightforward, but like the blue line seems a little bit smoother than the green one, typically. We were interested into also the how it protects against noise and attack. So basically here what you can see is I take my in gray it's my standard network, in green it's my Lipschitz. And what we did is we added some noises. Okay, so the x-axis is a noise, and the y-axis here is the deviation. So I take my input clean. Okay, it predicts let's say 50 degrees. Then I add some noise, and now it predicts me. It predicts I don't know, maybe 52 degrees. So the deviation in this case is 2. So we did this for all the data sets. And we just basically saw the average and the standard deviation. That's it here. What you can see is kind of very close, so which means that the vanilla is quite okay as well. But what is interesting to see is that the maximal deviation that we had was much more constrained by the Lipschitz than the standard neural network. And it's even bigger when the noise we choose was not completely Gaussian noise, but was a specific attack with the fast gradient sizing method, sign method, sorry. And in this case, we see that actually the maximal deviation we got for the standard neural network is way bigger, right? If you look at the scale, you'll see that the attack provides a bigger deviation, which is once again expected, while the Lipschitz constrains it much better. Okay, this is the kind of range that Decommand can provide. So once again, it's not super straightforward. What you can see is that the green area, which corresponds to the bound provided by Decommand, is broader than the Lipschitz and the sub. So the sub is when we just penalize the gradients. And so, yeah, for sure, vanilla is worse. Between Sobel and Lipschitz, it's kind of similar. But still a small advantage from Lipschitz. Last word for this part for PySR. This is the equation he found after all this time, which is not tremendous, right? But here I would like to show something. Even if it's slightly better than the linear regression, what is interesting to see is that this cosinus he found here, actually nobody can explain it. The experts don't know why there is a cosine here. What the hell is this? And I think this is worth mentioning, right? Because even if you have a tool which provides you a white box, does it make any sense, right? So for sure you can characterize it, you can derive it, and you can say, okay, this is a worst case situation. Definitely, but maybe from a physical point of view, it doesn't make any sense. So I thought it was worth mentioning it as well. Okay, I think it is close to the end. So let's last section. So when we have a topic where we need some robust AI, actually we saw that we have multiple solutions here. We have uncertainty quantification, we have scientific machine learning, formal methods, symbolic regression, and so on. And actually, this kind of solution can address a variety of use cases, from the non-operational, for instance, design optimization, typically we are using uncertainty quantification at Schaeffler for design optimization, to the safety critical, where we absolutely need bulletproof guarantees. So now, where are we in our work? So what we want to do is, we are just at the beginning of the journey. What we want to do now is develop new algorithm in each of these family, evidential neural network, and also investigate why our Kolmogorov neural network failed. But there are also plenty of other solutions. I never said that it was an exhaustive survey, right? Just a testimony of what we know, actually, at least in our team. So there is other family solution, data-centric robustness, invariant learning, and so on. And obviously, what I would like to do as well is trying to compare these different performance with other data sets, just to be sure that, yeah, it makes sense for any kind of data, because currently we lack of experience in a way. Okay, this is the end. I would like to make a special thanks, and I encourage you to look at these different libraries over there. So the Decommon to provide the interval band propagation, so with Melanie Dukoff at Airbus. The Lipschitz network library with Keras, developed by Frank Pamale in the context of DEAL and the ERT Saint-Exupéry. Both of these libraries are very plug and play, so no issue by using them. Uncertainty quantification, in my case, I used TensorFlow probability. It's already well documented, so no worries about it. And the CAN and PySR packages by Ziming Liu and Miles Kramer. Other than that, you know everything else. Okay, and I think with that, I'm done. So if you have any question.
Thank you very much, Laurent. It was a very nice presentation that take a lot of different dimensions of what the trustworthiness is, and I'm sure that many of the people in the audience have encountered some of these approaches in one way or the other. So I see that Bertrand has a question, so I'm gonna give him the.
Thank you. Yeah, it was really a very good presentation. Thank you very much. Very interesting and also very entertaining.
Thank you.
If you go back, I think it's the slide number something like 18 or 9, the one where you present all the results. This one.
Here we go.
Yes. It's not a very scientific question, but I see the second column family. I did not understand that the Kolmogorov was some kind of symbolic regression. So why do you qualify it as symbolic regression?
Yeah, so let's look at this. And this is my favorite algorithm, even if it doesn't work, but definitely it's my favorite one. So the whole idea of the Kolmogorov neural network is to train activation function itself. So actually,
the type of function. So you can change the type of function. So it's somehow symbolic, but it's also numeric somehow.
Yeah, definitely. So at the end of the day, what it's doing, it's actually each of these functions here are defined by spline coefficients. These spline coefficients are trained with descent gradients, like the weight of your neural network. And when these splines are defined, you are going to feed them with well-known functions, such as square.
Okay, so this is where the symbolic part comes.
Exactly.
Okay.
Exactly.
Okay. So it's some kind of hybrid between symbolic and traditional.
Correct.
Okay. It's like it has interpretability by design guarantees, but it's not like a purely symbolic framework either.
But in the same slide, you also say somewhere that the linear is symbolic, also something like that. Can we go back to that one?
Yes.
Yeah, because you say. No, Pia is linear regression. You call it symbolic regression too?
Yeah, because I mean, what I wanted to say is that at the end, you have like an analytical formula, right? So you can completely
Yeah, but
characterize
even
it.
when you train a standard network, you have an analytical formula. It's just a very complex one.
Yeah, sure, but like, I mean, when you go to a subject matter expert and you show them a linear equation or the equation of a neural network, I guarantee you for him it's not the same.
I think between something with a cosinus and a big neural network, there's a difference on interpretability. Yes.
Yeah, definitely, definitely.
Thank you.
I understand your point. It's I could remove it, but in my mind, it's like, okay, do I have like a readable analytical solution, so
No
to say?
problem. No problem. So why is it your favorite? Because it's not the best one.
Yeah, I know, but actually, I think it switches the paradigm actually from just training a bunch of weights. You train functions, and I found it so smart that that I really like it. So it just for the moment,
Okay.
maybe it's
It's a
maybe I
good
will
reason.
change my mind, but it's super interesting. Yeah?
Thank you very much.
Yeah, to come back to that, to what Bertrand said, in a way, we can still give a little bit of time to Kant to catch up with the literature, right? Because they're relatively new, like they are already more than a year, say, so they are not completely new.
Yeah.
But still, like many of the usual techniques that usually take time to find, they still haven't found it for this kind of networks. So I think that giving them time is all but fair for them. There is a question, a second question.
Yeah, thank you. Thanks for the talk. My name is Sujan. Also on this slide, the vanilla neural network, what kind of network is it? So my question is basically in the direction of, did you pick something reasonable where you can apply also the Bayesian approaches and so on, or is it the state-of-the-art method to solve this task?
No, it was like a very
for example,
simple.
like an LSTM, would you get better results?
Yeah, definitely. You would get better results. I actually, in the embedded framework we were in, we wanted to have the smallest network as possible. So I restricted myself to a very simple architecture, and which was convenient because of the time of training and so on. Plus, actually the prediction were really good with multi-layer perception. So no big reason to change at this stage.
Okay. And then regarding the data itself, I don't know if you already mentioned it. How do you ensure complexity of the data? You said there were different running regimes. Do you ensure that the test set contains all regimes, all complex scenarios, corner cases, and everything? Or is it more general run data set?
I would say it's more general because actually we took the data which was collected a few years ago without knowing we will do this study at this stage. So yeah, it's not an exhaustive data set, to be honest.
Okay. I'm just, maybe that helps your table. Maybe you can get Kants to perform better on certain scenarios where the vanilla network might fail because your data got complex and yeah.
Yeah.
Yeah, thank you. Thank you for the interesting talk.
Thank you.
Okay, Piotr, you can ask your question.
Thanks. Great talk.
Thank you.
I've been personally very interested in application of such models in the field of anomaly detection. And yeah, I wonder which one of those tools would have any useful properties for discovering anomalous behavior in a system. Since they have this regularization property, which encodes expected behavior of a system, can they detect when system starts to go like off rails? Perhaps this would be also a great tool for predictive maintenance related data collection.
Yeah, Yeah, exactly. The way I would see it is maybe a few years ago, the way we did it is by building an autoencoder and basically using the latent space to see if it was out of distribution, basically. But for sure, with, for instance, a Lipschitz network, I guess when you have even something in which is abnormal, you will see it even easier, I would say. So that would definitely worth a try. Agree.
Okay, there's a question in the chat. Maybe I'll ask. I just noticed right now. I'll ask my question and then I'll let the person that asked the question to ask it out loud if they can. Otherwise, I'll read it to you. I had a question about the Lipschitz neural network approach, and in particular the robustness and the fact of the kind of constraints that you have to also impose on the framework to work. Say, in here, I'm guessing that you're using the L2 norm to be able to provide the network, the Lipschitz analog of the network, right? And so the thing is that, of course, you will be able to provide, if you say create adversarial attacks on the basis of an L2 norm is all but normal, that that you actually find your guarantees. It's actually more like a sanity check than an actual robustness demonstration. The question is, between like these people that are talking between each other, and can we call it a really hard constraint if I can shift for the same epsilon, so the same perturbation budget, but I simply shift it to the L infinity norm, and I go and look for adversarial attacks that are precisely in that part of the L infinity ball that are not within the L2 ball. And I mean, it depends on the use case, but it is pretty realistic that an adversary will be mainly constrained by the epsilon. You increase the epsilon, it becomes visible, the attack becomes visible. But if you don't increase the epsilon and you just shift the norm, it is still somehow kind of like a same degree of realism. So I wanted your take on this, inherent limit of Lipschitz neural networks.
Yeah, it's getting trickier when we go into the details, right? But what you're right is that everything is built on a norm, and the norm, even of a matrix, is not that straightforward, right? We know what is the norm for a vector, okay, that's straightforward, but for a matrix, might not be straightforward once again. So what you're right is that these provide you a mathematical guarantee over a specific norm. So which doesn't mean that if you get attacked with another norm, you don't have this robustness with respect to this specific norm. That being said, I have the feeling that if you are kind of robust for a specific norm, you add some protection in a way. But I'm not aware of algorithm which protect over all of existing norms, definitely.
Okay, so well, I think I'll have other questions, but I'm going to read the question that was in the chat because they cannot turn the mic in, so I'll just take a second to do it. They say, thank you for the presentation. It was really insightful. I have a question about uncertainty quantification. What happens or might happen when the model encounters a driving cycle it has never seen before? Does it know it doesn't know?
So what you expect in uncertainty quantification is that when he goes in a region where he has not seen any cycles or close enough cycle, you expect the uncertainty to rise. That's all the purpose of the uncertainty quantification. So if your cycle fall in this area, you expect that the uncertainty will rise. Will it? That depends on how you coded your uncertainty quantification algorithm, but in theory, it should.
Okay. There's another question.
Yeah, I can read.
Okay.
One more question from me. This is not directly about the methods itself, but about virtual sensors, because I'm very interested. How do you, so since you're replacing a temperature sensor with the model here, how do you decide what else can be the inputs? Because I assume vibrations and so on are some kind of measurements that you would need to feed to this model. So I assume it's also a cost decision and everything, and probably there are some very cheap sensors that you can already integrate. But how do you ensure that every other related or relevant input is actually fed to the model?
Yeah. So in this specific use case, actually we had so here, for instance, you have the cycle power. Okay, the two first features, it's the torque and the speed, so it gives you the power. You have the current, and you have also the temperature of the oil and so on. So from expert point of view, they say basically with these features, you should have everything which is really important to predict it. Obviously, we had other features available, and basically we just did a sensitivity analysis, and this really confirmed this was the five important features.
Okay. Thank you. Yeah.
No worries.
And there's another question by Piotr. You can ask it.
Less of a question, more of an observation. So therefore, spike in uncertainty would potentially signal anomaly in the system being monitored.
So spine in. Can you repeat the question, please? Sorry.
If the system, sorry, if at inference time you seen a spike in uncertainty, this could be as a result of some kind of anomaly in the monitored system.
Exactly.
Yeah, I mean that is usually how OOD detection models that leverage you could do. Like you choose a threshold that is based on some uncertainty quantity being surpassed beyond a certain point, right? Which makes the whole system then interdependent, and which actually leads me to another question, which is, have you heard about uncertainty-aware adversarial attacks? These are adversarial attacks that put in their optimization loop not only something that tries to fool the model. It's like you try to not in the CAN world, but in the usual world in where you have like gradients. You take a positional, like you take the noise on the direction of positional gradients, right? Based on an optimization objective. So you include them by simply summing up a term that is going to maximize or minimize some uncertainty quantity, making the model to be overly confident or underconfident. And there are implementations already in place on these kind of things by people in Italy, if I'm not mistaken. Maybe you want to, since you are already like taking this holistic approach of testing these different things. A very nice thing would be to not treat them in isolation, but say like what happens if I use these attacks on my overall pipeline.
Okay. Good to know. I was not aware of this. So super interesting.
Okay, maybe I'll send you an email with the reference afterwards.
Yeah.